This is our final section in Chapter 3 on derivatives. However, Chapter 4 is all about derivatives, but in application problems, modeling the real world. In this last section in Chapter 3, we want to take a look at the derivatives of exponential functions and the derivatives of logarithmic functions. Exponentials and logarithms are two of the most important function types that we study. They have a wide variety of applications in all kinds of fields, from economics and finance to radioactivity, to population growth and decline, to the acidity of a substance or the strength of an earthquake. Because they have such wide application, they become very important functions in our study in calculus and engineering courses. We truly need to know what the derivative of these crucial functions is. Now, we're also going to learn another technique, which I alluded to in the last video. This technique is called logarithmic differentiation. This is something that will allow us to find the derivative of a function that has the variable both in the base and in the power. This is sometimes called a tower function, like x raised to the x power, or sine x raised to the x power, or x raised to the cosine x power. You have the variable x in both the base and the power. So it's not really a polynomial. It's not really an exponential. Those functions grow incredibly fast. They make exponentials look like they're standing still. They're one of the fastest growing class of functions that we study. We need logarithmic differentiation because we have to get the variable that's in the power down to the line so that we can take the derivative. We use logarithms to do that, since one of the properties of a logarithm is when you take the logarithm of something raised to a power, the power can be brought to the front of the logarithm as a factor. We'll exploit that in order to find the derivative of these tower functions. Then, after taking the natural log, we'll just do implicit differentiation, just as we did in the last section. Let me go ahead and cover for you now the few learning objectives that we have in this section. We're going to find the derivative of exponential functions, which actually I've already given to you. The derivative of e to the u, where u is a function of x, is e to the u with the chain rule times the derivative of u with respect to x. The exponential is one of our favorite functions to take the derivative of, as it's itself with the chain rule as well. Then we'll find the derivative of logarithmic functions. And then we'll use logarithmic differentiation to find the derivative of tower functions and to simplify some other more complicated functions that are not tower functions, but whose derivative can be found far more simply by using logarithmic differentiation. Now, most of the proofs for these particular derivatives are far beyond our ability at this point. We'll cover a little bit of proof-like things, but we're not going to be able to prove everything to you. You'll just have to take it on faith until you take a more advanced mathematics course. Now it's time for me to share my screen and we'll get started. E to the u is probably our favorite function to take the derivative of because it is e to the u times the derivative of u with respect to x. This is only true for e to the x. If the base is not e, say it's 5, like 5 to the x, the derivative isn't quite 5 to the x. It has something else attached, and we'll learn why in just a moment. Let's consider that number e a little bit more fully. It's called Euler's number, but it's spelled E-U-L-E-R. In case you were wondering, that's not Euler, that's Euler. A German mathematician named Leonhard Euler did a great deal of work with these special functions. And because of that, they named the exponential in his honor, E for Euler, E-U-L-E-R. He was, in fact, one of the most prolific and amazing mathematicians of all time. Many mathematicians do their best work in their early 20s and throughout their 20s, and then they sort of peter off on great ideas after that. This man was blind the last 20 years of his life, and he produced just as many valuable, important theorems at the end of his life in his 80s as he did at the beginning. He was a phenomenal mathematician and dictated what he could see in his head to his assistant. Let's now look at his number. We're going to define Euler's number, the italicized E, to be the unique positive number for which the derivative of that number raised to the x power at 0 is 1. In other words, on the graph of e to the x, when x is 0, the slope of the tangent line is going to be 1. That gives us f prime of 0 equal to 1. Now, there are other useful definitions for E. I gave you another one just for fun because we're going to see it coming up again in chapter 4, and I thought I'd preview it here. You can also define E as the limit as x approaches infinity of 1 plus 1 divided by x, all in parentheses, raised to the x power. Notice we have the variable inside and we have the variable in the power. This is one of those kinds of functions I was telling you about. When we look at this, the limit of this function goes to the number e. E is an irrational number. It is about 2.71828, There is no pattern, in spite of the initial 4 that repeat. There is no pattern, and it goes forever. It's an irrational number. However, it's not algebraic. And by that, I mean it's not the solution to a quadratic equation with real number coefficients. When we're looking at this, or rather with integer coefficients, when we're looking at E, think of it as about 2.7-ish, and as a very special transcendental number. Transcendental means it's not algebraic, meaning it didn't turn out to be the square root or cube root of anything. It's just E, kind of like pi or phi. Now let's look at the graph of e to the x. The graph of e to the x, you should remember from your pre-calculus days, is that it does this. As it approaches negative infinity, it approaches the x-axis, 0. It crosses through the y-axis at the point 0, 1, and then it grows incredibly fast. We often describe compound interest using e. We also describe exponential growth and exponential decline in growth using E. This graph of E here makes it look like it's not as steep as it actually is. That's because they've changed the scale. Don't be fooled. E grows incredibly fast. Not as fast as x to the x. When we look at this graph, we see that the slope of the tangent line is 1 at the point 0, 1. This was the way we defined E. Now we want to go ahead and talk about the derivative. E to the x is called the natural exponential function. The natural because it's the natural base. When something grows, well, exponentially fast, the best base to use is E. Not 5, not 3, but E. E to a power represents this exponential growth or decay, like in radioactivity. Because of that, the logarithm base E is called the natural logarithm, since it uses the natural base, Euler's number E. We write natural log ln of x. The base, when you write Ln, is known to be E. It cannot be anything else. It's also correct to write log base E of x. It means the same thing. Now let's look at the derivation of the derivative of some number raised to the x powered. We're just going to give a brief overview to what we have here, and then we'll get a little bit more into the formulas for the derivative. We're going to define a function, uppercase b, to be this positive number raised to the x powered. Again, we need the base to be positive because we want to make sure that we're not raising a negative number to an even radical. That would cause it to be imaginary, and it wouldn't graph on a real graph. We'd like our function to be connected and continuous, so we require that the base be strictly positive. We're going to assume, without proof, this is one of those things we can't prove yet, that this function, which consists of base b to the x power, the derivative at 0 does exist. Then we can go ahead and write the definition of the derivative as h approaches 0. This would give us b to the x plus h minus b to the x, all divided by h. And since we know we want the derivative at 0, we can substitute 0 in place of x. This gives us b to the 0 plus h minus b to the 0, all divided by h. As you know, a constant raised to the 0th power other than 0 is going to give you the number 1. And this results in b to the h minus 1 divided by h. We know that this is a representation of the derivative at 0, which we are assuming exists. Now we want to take a look at the derivative at any arbitrary value of x other than at 0 and see if we can come up with a formula. In this case, we rewrite the definition of the derivative, but at a general value x, not specifically at 0. This gives us the limit as h approaches 0 of the difference quotient, b to the x plus h power minus b to the x, all divided by h. Of course, if you substitute 0 for h, you get that indeterminate form. We use the property of exponentials that if the base is raised to the sum of two powers, that it's actually the product of the base to each individual term. Normally, we apply this rule in the reverse. X squared times x cubed is x to the 2 plus 3, or x to the 5th. But we can apply it in this direction as well. X to the 5th is equal to x squared times x cubed. In this case, we rewrite b to the x plus h power as b to the x times b to the h. Once we do that, we have a common factor of b to the x in the numerator, which we factor out. Notice that the b to the x does not depend upon h. Because of that, we split it up into two separate limits. Because it does not depend on h, the limit of b to the x is b to the x. Then we're left with the limit of b to the h minus 1 over h. We know, however, that in this case, this represents the derivative at some arbitrary point. This is the derivative at 0 specifically that we found earlier. We can replace this second limit with the value of the derivative of the function at 0. Now, the next thing we want to do is put this together and come up with a formula. We assumed that the derivative at 0 exists, and this tells us that the derivative of b to the x at an arbitrary point is b to the x, but multiplied by its derivative at 0. Now, it won't be this complicated later. You'll see exactly what that turns out to be. For our particular function, e to the x, we know that the derivative at 0 is 1 by definition. Because of that, for this formula, we have b to the x times the derivative at 0, which is 1, and we get e to the x times 1, which is e to the x. We'll discuss what that derivative at 0 becomes for a base other than e in just a few minutes. Let's take a look at the theorem about the derivative of e to the x. We let e to the x be the natural exponential function, then the derivative is e to the x. It's true, but not a very helpful form to memorize. Instead, memorize the u form. The derivative with respect to x of e to the u, where u is a function of x, is e to the u du dx. Memorize the form that has the chain rule already built into it. You can also write it as the derivative with respect to x of e to some function g of x, which gives you e to the g of x power times the derivative of that power, g of x. Let's take a look at our first example, which is x e to the 2x. Let's go ahead and take the derivative of it now. We definitely have a product between x and e to the 2x, so we'll apply the product rule. X is going to be my f, and e to the 2x is going to be my g. So I'm going to compute the derivative of h prime of x, to be the derivative of x, 1, times e to the 2x, unchanged. This is f prime g, plus, now I need g prime times f. The derivative of e to the 2x is e to the 2x times the derivative with respect to x of 2x. Then to multiply by f, I multiply by the x. The x should really be moved around to the front so you don't mistakenly think you need the derivative of it. This will give me e to the 2x plus, well, the derivative of 2x is 2, so I get 2x e to the 2x. Now, later this semester, we'll be doing some things where we'll want to know where the derivative is 0. E to a power is never 0 unless it's been shifted up or down by adding a constant to the exponential. So when we see that the exponential is common to two terms, we'll often factor it out because it will never give us an x-intercept. The x-intercept, if there exists one for the function h prime, must be coming from 1 plus 2x. Let's now look at the next example. In example 2, we're given that a of t is 1,000 times e to the 0.3 t. This describes the mosquito population in an area after t days. We want to know what the rate of change of a of t is after 4 days. A probably represents amount. This is the number of mosquitoes present at a particular time. We want to know how fast the number of mosquitoes is changing after 4 days. In order to do this, we'll first take the derivative. When we take the derivative of a, in this case, the 1,000 is constant, so we can just tack it on the beginning. Then the derivative of e to the u is e to the u times the derivative of u with respect to, well, in this case, t. This is going to give me the derivative of 0.3t, which is 0.3. Then I multiply that by the 1,000 to get 300. Now I want to know what the rate of change is after 4 days. So I replace t with 4 in the derivative formula and compute. This will give me 300 times e to the 1.2 power, which turns out to be approximately 996. What does that mean? That means that on the 4th day, we're adding 996 mosquitoes a day. That's rather alarming. Let's now look at the theorem describing the derivative of b to the x. When we look at this one, the b could be e. It will work for e, but in general, what we're expecting instead of b is we're expecting something like 2 to the x, where the base is not the value e. We're going to let the y equal b to the x, where the base is a positive value and not 1. 1 to any power is 1, which just gives us a horizontal line, which is, well, boring. Then we take the derivative of both sides. This gives us dy dx on the left, as we learned in implicit differentiation, and the derivative of b to the x is b to the x times the natural log of the base. Now, why does this also work for e to the x? So if I want to take the derivative of 2 to the x, I get 2 to the x times the natural log of 2, where the natural log of 2 is a constant. That means that the derivative with respect to x of e to the x is actually e to the x times the natural log of e. But if you remember your rules from pre-calculus or college algebra, the natural log of e is 1, which gives me e to the x. Incorporating the chain rule, if we were to have u instead of x, we would have b to the g of x times the derivative of g times the natural log of the base. Or as I would like you to memorize, the derivative of b to the u, where u is a function of x, is b to the u, natural log of the base, times du dx. That's the form you should memorize. Let's take a look at the proof now. We start with the original equation, y equals b to the x. Then we apply a logarithmic property, which says if you take the natural log and then take it and raise e to that power, they undo each other. They're one-to-one inverse functions. So e to the natural log means you actually haven't done anything. It's like adding 5 and subtracting 5. You've done nothing. B to the x is equivalent to e to the natural log of b to the x. But there is a logarithm rule that says if the answer part following the logarithm has a power on it, I can pull the power to the front. The logarithm is itself a power, so we're multiplying the two powers together. Natural log of b is a power and x is a power. These are both on e. Now we take the derivative of this on both sides to get dy dx equals e to the x times the natural log of b. But the natural log of b is a constant. So the derivative of x times the natural log of b, well, the derivative of x is 1, so times the natural log of b just gives us the natural log of b. And then we come back to where we started, that e to the x natural log of b is actually b to the x, and it's now multiplied by the natural log of b. Let's go ahead and apply the rules that we've learned so far to these following different functions. We'll start with the first two, then you'll pause the video to work the others out. Then we'll turn the video back on and we'll compare our results. The first one is an exponential function, 5 raised to the x power. The base is 5, not e, which means when I take the derivative, I do get the exponential, but I also get the natural log of 5. You could write the natural log of 5 at the front of the exponential or at the back. For the second one, we have 4 raised to a power that is a function of x, 2x minus 3. To find the derivative, we end up with exactly the same exponential, 4 to the 2x minus 3, times the derivative of that power. This is the chain rule. The derivative of 2x minus 3 is 2, so I end up with a 2 times 4 to the 2x minus 3. You're going to have to put the 2 either in parentheses or put a dot for multiplication, since otherwise it will look like 24. Only the 4 is being raised to the power, not the 2. And you cannot multiply them together because exponents are done before multiplication. Go ahead and pause the video now to work out the ones that are left. There's a page and a half of these, so I expect it will take you a while. Then turn the video back on and we'll talk some about these derivatives. Let's now take a look at the product rule in this particular one, x squared e to the x. We apply the product rule and get 2x times e to the x plus g prime f. The derivative of e to the x is e to the x, since the derivative of x is 1, times x squared, which gives us 2x e to the x plus x squared e to the x. There is a common factor of both e to the x and x. You could factor them both out, or you could just factor out the e to the x. I'll leave that up to you. In the next one, at the end of this page, we have e to the negative x divided by x. In this case, we could apply the quotient rule, or we can write the single term in the denominator to the negative 1 power and apply the product rule. That's the method I chose. The derivative of e to the negative x is e to the negative x times the derivative of negative x, which is a negative 1. Then we multiply by x to the minus 1. For the second part, we take the power rule to the x to the minus 1, giving negative 1 x to the minus 2, and multiply by the exponential. When we look at the next thing, notice that both terms are negative. I chose to factor out the negative and the exponential, e to the negative x, which left me 1 over x plus 1 over x squared when I moved the factors with negative exponents to the denominator. Notice that this means I have a 1 over x, which is also common, which I could factor out as well. Notice also that e to the negative x is 1 divided by e to the x. So you could write the answer in several different formats. You do want to simplify somewhat, because you don't want to leave your professor to be doing your algebra for you. That makes for a really cranky professor. Let's now take a look at this first one, the square root of e to the 2x plus 2x. The derivative of the square root of u is 1 over 2 the square root of u du dx. This is the chain rule form. We apply this to our function, and then we take the derivative of what was under the radical. This invokes the chain rule, giving us the exponential e to the 2x times the derivative of 2x, which is 2. Notice we have a common factor of 2 in the numerator and a single factor of 2 in the denominator. Factor the 2 out of the numerator to get e to the 2x plus 2, or e to the 2x plus 1, and then cancel the 2. The next one is an interesting function. This one actually has a name. It's called the hyperbolic tangent function. It's not actually a trig function at all. They get the name hyperbolic trig functions because the formulas for their derivatives and their definitions somewhat, though not completely, follow the rules for the basic 6 trig functions. We do also have a definition for hyperbolic sine, which you'll see here in the lower right. E to the x minus e to the minus x divided by 2. It's not a trig function. It's an exponential, but it behaves sort of like a trig function. Notice that the hyperbolic cosine, cosh of x, notice the h following the trig name, is e to the x plus e to the minus x divided by 2. It's very close to the definition of hyperbolic sine or sinh. Notice that the definition for hyperbolic tangent, which is our function, is the ratio of sinh to cosh. This is why they got called hyperbolic trig functions. They're not trig at all, they're exponentials, but their definitions sort of follow the trig rules. So we call them hyperbolic trig functions. These are things that describe, for example, if I were to take a string and the string had some weight and it was suspended between 2 points, like a power line between 2 posts. The shape of that particular thing is defined and described by what's called a catenary function, which is a hyperbolic trig function. So any kind of wire or cable that's suspended under its own weight, that shape that it forms is not actually a parabola. It's actually a hyperbolic trig function. In order to take the derivative, I chose to apply the quotient rule because they looked kind of complicated. The product rule would work as well and would be just as good. I kind of ran out of room, but you can see what I've written up here. Notice that when I take the derivative of the denominator, the derivative of e to the x is e to the x, but the derivative of e to the negative x is negative e to the negative x, because the derivative of negative x is going to be a -1. This gives me a -1 in here, which changes the sign of that term to plus. Notice that the numerator already, the top then gives me a double negative, which gives me a plus, which matches what I had in the denominator, which gives me 2 of that factor, or squared. I will need to multiply that out, but we'll hold off on doing that. And I subtract the derivative of the denominator times the numerator. The derivative of the denominator gets a minus e to the minus x due to the chain rule, which gives me 2 of this factor, so it's also squared. But it's not the same factor because the sign in the middle is different. It's all divided by g squared, but I cannot cancel it because I don't have a common factor in the numerator. Now I multiply these out by multiplying their binomials together. In the middle term of the first one, I get 2 e to the x times e to the minus x. I would get minus 2 e to the x, e to the minus x in the second binomial. When I'm looking at this, remember that when the base is the same and you're multiplying, you add the powers. So this combines to give me e to the x minus x, which is e to the 0. But e to the 0 equals 1, which means that those terms simplify to 2 and minus a -2 because of the subtraction between them. Minus a -2 makes it plus 2. And then I have cancellation of terms. Everything but the 2 constant terms cancels. And I end up with 4 divided by the denominator squared. Let's now look at the last 3 problems. I have 10 to the x divided by the natural log of 10. This is actually a short problem because natural log of 10 is a constant. So I can pull it to the front as 1 over the natural log of 10, and then just take the derivative of 10 to the x. The derivative of an exponential is the exponential times the natural log of the base. The base is not e, so it's not 1, it's natural log of 10. And these constants cancel, and I get 10 to the x. This next one is an interesting problem. We have 3 raised to the power sine of 3x. In order to find the derivative, we take the derivative of the exponential, which is the exponential, unchanged, times the derivative of the power for the exponential. The derivative of sine is cosine. Chain rule tells us to leave the inside 3x. Then we multiply by the derivative of 3x, which is 3, which gives us 3 cosine of 3x times 3 to the sine of 3x power. Notice that we have 2 things that have a base of 3, and they're multiplied together. Even though it's not written, I could write a 1 on the 3 that is a constant factor. Then, because the bases are both 3, I could add their powers and get cosine of 3x times 3 to the 1 plus sine of 3x. Finally, we want to look at this problem at the bottom. We have a power function, x to the pi, which means we'll do the power rule. Remember, the power rule works as long as the power is a real number. Pi is irrational, but it is real. Then we have it multiplied by an exponential, where they've swapped the variable. We've got pi raised to the x power. Pi is a constant. So when we take the derivative of this part, we'll need the natural log of pi. They're multiplied together, so this is product rule. The derivative of x to the pi is pi times x to the pi minus 1 power. Then I multiply by pi to the x. Then I take the derivative of pi to the x, which is pi to the x, times the natural log of pi, which is a constant. And then I multiply by x to the pi, the power function. Again, in the first term, I have pi to the first and pi to the x. That means I can write them together as pi to the 1 plus x, or x plus 1, times x to the pi minus 1, plus pi to the x, x to the pi, times the natural log of pi. There are no common factors there, unless you want to split up the x to the pi minus 1, which is a possibility, but we'll leave that for another day. I think we've done the derivative of exponentials to death, so it's probably time to go ahead and talk about the derivative of the natural log function and the derivative of a log with a base other than e. Most of the time, in most of our applications, we use natural log, but in some applications, like earthquakes and the pH scale for the acidity of a quantity, we actually use a base other than e. Let's now take a look at the definition of the derivative of natural log of x with base e, Euler's number. X has to be strictly positive because natural log will not accept 0 or a negative number in the argument. If we set that equal to y, then the derivative of natural log of x is 1 divided by x. This is an example of a function where it started logarithmic and the derivative of it is algebraic. Like the inverse trig functions, the derivative of a logarithm is not a logarithm, it's algebraic. We're going to incorporate the chain rule now and say that the derivative of the natural log of u is 1 over u times du dx. You take the reciprocal of what's inside the argument to the natural log, and then you multiply by the derivative of what was inside the natural log. The second form is the one that you should commit to memory. There is an error in the textbook. I've noted it here in blue. I think in the textbook it may have f of x or something, but it should be g of x greater than 0. Let's look at the proof of this theorem. We start with the original statement that y is the function natural log of x. Then we convert it to logarithmic form using our skills from pre-calculus to write it as e to the y power equal x. Next, we're going to take the derivative of both sides of the equation since we know what the derivative of e to the y is. The derivative of e to the y will invoke implicit differentiation, and I'll get the exponential e to the y times the derivative of the power, which is dy dx. The derivative of x is just 1. Now I can solve for dy dx to get 1 over e to the y. But by definition, in the second line, e to the y is x. So I can replace it, and I get what I was looking for. The derivative of natural log of x is 1 over x. Let's go ahead and look at this formula as well. In an earlier section, we studied the derivatives of inverse functions, and we found that when functions were inverses of one another, to find the derivative of one of the functions, I could take its inverse function's derivative and substitute the original function inside. In this case, I can find out the derivative of the original function natural log by looking at its inverse function e to the x. The derivative of e to the x is e to the x, but I substitute the original function natural log of x inside. And remember what I said earlier. If you take the logarithm of something and then you take e to that power, you've done nothing. When the e and the natural log are touching one another with no number or sign between, they cancel in a sense. They undo each other. And you get back out of it whatever argument is inside natural log, which is x. Now we'll look at some examples. We'll work through a couple of these, and then I may let you work on some on your own. Let's take a look now at the natural log of 3x plus 2 raised to the 5th power. First, you'd raise it to the 5th power, and then you would take the natural log. So natural log is the outside function, and 3x plus 2 to the 5th is the inside function. It's actually nested 3 deep because 3x plus 2 is the innermost. So in this case, we have natural log of x as the outside. Then we have x to the 5th as the middle layer. And then we have 3x plus 2 as the inside function. Let's take the derivative now using chain rule. F prime of x is going to be the derivative of natural log on the outside, freeze the inside. Derivative of natural log is 1 over u, which will give me 1 over 3x plus 2 to the 5th power, times the derivative of what's on the inside, which is the 3x plus 2 to the 5th power. And I apply the chain rule to that step to get 1 over 3x plus 2 to the 5th times 5 times 3x plus 2 raised to the 4th times the derivative of what's inside of that, which is 3. The 5 and the 3 can multiply together, and that will give me 15, 3x plus 2 to the 4th power divided by 3x plus 2 to the 5th power. Everything in the numerator is factored. The plus sign is buried inside parentheses, so I can cancel if I have some common factor. 3x plus 2 is common between the numerator and the denominator, so I can go ahead and cancel 4 of them to end up with a final answer of 15 divided by 3x plus 2. Let's now take a look at the next example, number 5. I want you to work this one out, then turn the video back on to compare your answer. And we'll take a look at example 6 together. So let's take a look. To find the derivative, I identified the outside function as the natural log and the inside function as 4x cubed plus x, the polynomial. The derivative of the outside is 1 over u times the derivative of the inside. Then I take the derivative of the inside, and I got 12x squared plus 1 divided by the inside 4x cubed plus x. There is a common factor of x in the denominator, but it is not common to the numerator because of the plus 1. So there's not much point in factoring it out. So I would leave it as is. Let's now take a look together at example 6. I have e to the x cubed multiplied by natural log of x. There are actually 2 approaches to this that we can use. I'll show you the first, which is the harder way, and then I'll show you the second. When we look at this particular one, we're going to start by saying that the derivative with respect to x of the exponential, e to the x cubed natural log of x, would be the exponential, e to the x cubed natural log of x, times the derivative with respect to x of x cubed times natural log of x. Now, that invokes the product rule. So the next step, we still have the exponential present, and it will just continue to follow along, multiplied by the product rule result, which is 3x squared times the natural log of x, plus 1 over x. The derivative of natural log is 1 over u, and the derivative of x is 1, times x cubed. We can simplify this term right here, and we end up with e to the x cubed natural log of x times the quantity 3x squared natural log of x plus x squared. There's a common factor of x squared, which we could factor out. I'm going to hold off on that for just a second because I want to cover an easier way, and then I'll simplify that last expression. What's another way of looking at this problem? Notice that we have something between the e and the natural log of x, namely the x cubed. But there is a logarithm property that says if the answer part had a power, you could bring the power to the front. That must be what the x cubed is. But it also means you can put it back inside. So what I'm going to do is I'm going to simplify my function, e to the x cubed natural log of x, by rewriting it as e to the natural log of x raised to the x cubed power. Now what do? Well, on this one, the e and the natural log would cancel each other out. Then I would be left with x to the x cubed power. This is what we call a tower function, where the variable is in both the base and the power. In fact, I have a power on the power. These grow incredibly fast in most cases, unless they're multiplied by a constant that's very small. They grow really rapidly, far more rapidly than an exponential. We're going to need natural log in order to get our hands on the x cubed. In other words, this one can't be done yet with the techniques we've been learning because we haven't talked about how to deal with tower functions. To solve this problem, we would need to use the technique of logarithmic differentiation. We're going to pause on that right now, and I'll take a look at this one here and see if there's a way to simplify it. Again, coming over here, I could factor the x squared out, and I could move the x cubed on top of the x as the power inside the logarithm. Whether you choose to do so is up to you, but I recommend at a minimum factoring out the common x squared factor to get something that looks like this. Remember that it does leave a placeholder of +1 behind when you factor out that common x squared. We'll come back to this problem after we've learned logarithmic differentiation, and we'll solve it. Let's now look at example 7. Example 7 is the product of two functions, x squared and natural log of 9x. Pause the video and find the derivative. Let's compare results. This is actually a relatively short problem where you have to apply the product rule. The derivative of x squared is 2x, and we multiply by the second factor. Then we take the derivative of natural log of 9x, which is 1 over the 9x, times the derivative of 9x, which is 9. And then we multiply by the first factor, which is x squared. The 9 will cancel, and one of the x factors from the numerator will cancel, leaving a plus x for the second term. If you were looking for zeros, you could factor out the common factor of x. I don't expect my students to factor out common factors when they're looking for the derivative unless they have a purpose for doing so, such as looking for a zero or x-intercept of the derivative. We've dealt with the natural logarithm and how to find the derivative of natural log with the base e, Euler's number. But what if our base is not e? What if we have log base 7 of x, as you would find in the pH scale in chemistry, or log base 10 of x, as you would find in the Richter scale for the magnitude of an earthquake? It turns out that, like with the exponentials, when the base is not e, you're going to get a natural log of the base involved. It makes sense, since the formula for the derivative of natural log is 1 over u, that natural log of the base shows up in the denominator, and in fact it does. The derivative then of log base b of u becomes 1 over u times the natural log of the base, which is a constant, times du dx. This is the form you need to memorize. Let's go through the proof now. We set our function y to be log base b of x. For example, we could have log base 7 of x. Then we switch from this into exponential form. This is logarithmic form, and switching would give us 7 to the y equals x. This gives us b to the y equals x in general. Now, if we want to, I need to get my hands on the y, since that's what I'm trying to find the derivative. It makes sense, after applying the one-to-one logarithmic function to both sides, that it should still be equivalent. What I want to do now is go ahead and apply the natural log to both sides of the equation. So, for example, in my set, I'm going to have the following. The natural log of b to the y equal the natural log of x. In our example, we would have the natural log of 7 to the y equal to the natural log of x. That rule with logarithms that allows you to pull the power on the answer part to the front allows us to get our hands on the y. The next thing we want to do, of course, is go ahead and either take the derivative or divide both sides by the natural log of the base. The y represents our logarithm. We want dy dx. So the next thing we're going to do probably is isolate the y and write the natural log of x divided by the natural log of the base. Or in our example, the natural log of x divided by the natural log of 7. Now I'm going to take the derivative. Remember that the natural log of the base is a constant. And you can see that here because natural log of 7 is a constant. That means I can factor it to the front and take the derivative of natural log of x, which means that the derivative of y dy dx is 1 over x times the factor 1 over the natural log of the base, which gives me 1 over x times the natural log of the base. Over here, in my example, I would end up with dy dx equal to 1 over x times that natural log of 7 constant. Let's go ahead and take a look at several of the examples. I believe that all 3 of these are something that you could handle on your own at this point. So I want you to pause the video, work out 8, 9, and 10, and then turn the video back on. Go ahead and write down 8 and 9 now. And here's 10. Let's look at example 8 now. When we look at example 8, we have the logarithm of secant x, but it's not natural log because it spells out log. There's no base written, so the base must be 10, the common log. I rewrote it as log base 10 to make it more explicit. Then I apply the derivative. This gives me 1 over the argument to logarithm times the natural log of the base in the denominator. This then has to be multiplied by the derivative of the inside function as part of the chain rule. The derivative of secant x is secant x tangent x divided by secant x times the natural log of 10. Secant x is canceled, and you get tangent of x divided by the constant natural log of 10, which represents 1 number. For example 9, I had a function nested several layers deep. I first identified that the outermost layer was the log base 7. In the middle, I had something to the 5th power. And the very innermost layer was the polynomial 6x to the 4th plus 3. I apply the chain rule more than once in order to find the derivative of this function. The derivative of a logarithm is 1 over the argument, exactly as it is, in the denominator times the natural log of the base, which was 7. Then multiply by the derivative of what was inside the logarithm. Note that this part is in the numerator. The derivative of something to the 5th is 5 to something to the 4th times the derivative of what was inside that power function, which is 6x to the 4th plus 3. Notice that we have a common factor, and all my addition and subtraction is buried in parentheses. So I can reduce the 6x to the 4th plus 3 to the 4th power over the same to the 5th power to get one of them in the denominator. Then I take the derivative of 6x to the 4th plus 3, which is 24x cubed. Finally, I go ahead and I multiply out the numerator, and then I notice that I've got a 6 plus 3 in the factor in the denominator, which means I have a common factor of 3. I factor it out to get 2x to the 4th plus 1, also times the natural log of 7, and the 3 I factored out. The 3 will reduce with the 120x cubed in the numerator, to give me a final answer of 40x cubed divided by the product of the natural log of 7 and the quantity 2x to the 4th plus 1. Let's look at example number 10. 10 has both the product rule and a 3-layer chain rule. The chain rule has log of base 3 for the outside, 7 to the x for the inside, middle, and x squared minus 4 for the innermost layer. This is multiplied by the exponential function 2 to the x. So first I apply the product rule. Derivative of 2 to the x is 2 to the x, natural log of the base, which is 2. Leave the logarithm base 3 part alone. Plus, now I've got the first times the derivative of the second. I wrote the 2 to the x at the front, so I didn't lose track of it, because I knew I was going to have to apply the chain rule multiple times. When I go ahead and apply this, remember that because the base was not e, I get a natural log of the base as a factor in the denominator. Then I multiply that by the argument to the logarithm, which was 7 to the x squared minus 4. I have to multiply by the derivative of that 7 to the x squared minus 4, which gives me 7 to the x squared minus 4, times another natural log of 7 because the base is not e, times the derivative of x squared minus 4, which is 2x. Notice this gives me the exponential 7 to the x squared minus 4 in both numerator and denominator, so they cancel. This is the final result that we get here. I could, if I wanted, combine the two factors, 2 to the first and 2 to the x, and write 2 to the x plus 1 times x times the natural log of 7 divided by the natural log of 3 for the second term. With the first term, 2 to the x times natural log of 2 times log base 3 of 7 to the x squared minus 4 power. We're finally ready to talk about logarithmic differentiation. Logarithmic differentiation allows us to take the derivative of tower functions like we saw earlier when we ended up with a variable in the base and in the power. It also allows us to simplify more complicated expressions and find the derivative somewhat more simply, even when they're not, in fact, tower functions. Let's go ahead and look at the rule now. To do logarithmic differentiation, we want to follow the following steps. First, we're going to write it as y equal to some function. And we're going to take the natural logarithm of both sides of the equation. We choose natural log because it has the simplest derivative. The natural log of e is 1. So we just get 1 over u du dx. This allows us to write the natural log of y equals the natural log of h of x. Let's go back to the problem we did earlier and pull that problem down here as an example. I'm trying to remember where it was. 6. Yes, there it is. Y equals x to the x cubed. Let's write that over here. In order to use logarithmic differentiation, first I want to take the natural log of both sides. This will give me the natural log of y equals the natural log of x to the x cubed power. Now I'm going to use the properties of logarithms to expand that as much as I possibly can. And by that, I mean I'm going to pull this power down to the front so I can get my hands on it. This allows me to write the natural log of y equals x cubed times the natural log of x. Now that I've taken the natural log of both sides and simplified the side that had the tower function, I'm ready to go ahead and take the derivative. Note I haven't done the derivative yet. I've just taken the natural log of both sides of the equation. Now I apply the derivative to both sides. The derivative with respect to x of the natural log of y will give me 1 over y dy dx. On the other side, I'll have to invoke the product rule. When I invoke the product rule, this is going to give me 3x squared times natural log of x plus 1 over x times x cubed, which reduces to x squared. Let me simplify the problem first. I end up with 1 over y dy dx equal to 3x squared natural log of x plus x squared. The next thing I want to do is move the y to isolate the dy dx as we did when we did implicit differentiation. That is in fact what this is. This will give me dy dx equal to y times the quantity 3x squared natural log of x plus x squared. I could factor out the x squared if I wanted to. I know what y is, however. It was my original statement. I know y is the tower function x to the x cubed power, so I can replace it. I'll also factor out the common x squared. X squared times x to the x cubed power times 3 natural log of x plus the placeholder 1. Now, I do have two factors with base x raised to powers. If I want, I can combine them by adding them together. And this would lead to x to the x cubed plus 2 power times 3 natural log of x plus 1. We actually ended up with an explicit formula for the derivative, which looks much easier and less complicated than the one we had previously. Let's now apply it to another situation where we might want to use logarithmic differentiation. When we have a rational function, the ratio of two polynomials, where the polynomials are raised to relatively large powers, it turns out that instead of applying either the quotient rule or the product rule, that we're better off doing logarithmic differentiation. What we're going to do is let y equal this rational function that you see here, x plus 1 to the 10, divided by 2x minus 4 to the 8. The next thing we want to do is take the natural log of both sides. Always use natural log so your derivatives are easier. Then we're going to use the logarithmic properties of quotients and powers to simplify this and expand it as much as we can. We can apply the rule that the natural log of a quotient is the difference of the numerator minus the denominator, the natural log of the numerator minus the natural log of the denominator. Then I can pull the power on each part to the front. This gives me 10 natural log of x plus 1 minus 8 natural log of 2x minus 4. And I noticed that I had a common factor of 2, so I rewrote 2x minus 4 as 2 times x minus 2. This gives me the natural log of a product, which splits into a sum, but it's being multiplied by a negative 8. So I end up with negative 8 natural log of 2 minus 8 natural log of x minus 2. Keep in mind that negative 8 natural log of 2 represents one real number, a constant. Now that we've taken the natural log of both sides and we've expanded the natural log as much as we can, we're ready to take the derivative. When we take the derivative, we apply it to both sides of the equation, which is going to lead to 1 over y dy dx on the left when we take the derivative of natural log of y. On the right, remember that the 10 at the front and -8 at the front of the natural logs are constants, which can be pulled to the front. The derivative of natural log of x plus 1 is 1 over x plus 1 times the constant 10 times the derivative of x plus 1, which is 1. The derivative of -8 natural log of 2, since it's a constant, is 0. And we apply the derivative formula to -8 natural log of x minus 2 to get -8 divided by x minus 2. Then we're going to multiply both sides of the equation by y. Then we replace y with the original representation of y, which gives us this expression here. How far you go from this point depends on your professor and how complicated it looks and whether you think you can make it simpler. In this case, I thought maybe I could make it simpler. So what I did instead was I combined different terms here and I rewrote them so that I could get common denominators. Now, when I did this, I continued working and notice at some point, I took the 2 that was a common factor in the 2x minus 4 to the 8th power out of that power. But if you pull the 2 out, it's really 2 to the 8th since it's there 8 times. And that gives you 2 to the 8 times x minus 2 to the 8th. After more simplification, you can get this at the bottom. I don't know that it's any better than what you see up here. It's just different. Let's now take a look at our last 4 examples. We want to use logarithmic differentiation to find the derivative of the basic tower function x to the x. Let's go ahead and do that now. In order to find the derivative of x to the x, we first take the natural log of both sides to get natural log of y equals natural log of x to the x power. Use the log properties to pull the power x to the front and multiply it by the natural log of x, the argument to natural log. Now I'm ready to take the derivative. I take the derivative with respect to x of both sides of the equation, which is going to give me the product rule on the right side since I have x times natural log of x. This will give me 1 over y dy dx, and the dy dx is what I'm looking for. The product rule gives me 1 times natural log of x plus 1 over x times 1 times x, which reduces to 1. This gives me dy dx equal to the natural log of x plus 1 times y. Then I replace y with the original statement of x to the x times the natural log of x plus 1 quantity. That's the derivative of that tower function. And notice that it is actually an explicit formula. There's no y left in the derivative. I'll let you now turn your attention to the next 2 problems, 12 and 13. 12 is a type of tower function because we have the variable x in the base and the power put inside trig functions. This is sine x raised to the tangent x power. Apply logarithmic differentiation to find the derivative. In 13, your function is x raised to the square root of x power. And then we want to find where it has a horizontal tangent line. A horizontal tangent line has a slope of 0. So you're being asked to find where the derivative is equal to 0. Go ahead and pause the video and work them out now. Let's now look at example 12. In example 12, we have the function sine of x to the tangent of x. We take the natural log of both sides and use natural log properties to pull the tangent of x to the front, multiplied by the natural log of sine x. Then we take the derivative with respect to x of both sides, and the derivative of natural log of y becomes 1 over y dy dx using the chain rule. We apply the derivative to the right using the product rule, where the derivative of tangent is secant squared, multiplied by natural log of sine x unchanged, plus the derivative of natural log of sine x, which is 1 over sine x, times the derivative of sine x, which is cosine x, times tangent of x. Notice that cosine divided by sine is actually cotangent. Cotangent and tangent are reciprocals, so their product gives me a 1. I can then move the y to the right side and replace it with the original function, sine x to the tangent x power times secant squared of x times the quantity natural log of sine x plus 1. We now want to look at example 13, where we were supposed to find where it has a horizontal tangent line. This is similar to example 11 in that it is a relatively straightforward tower function, but this time the power is the square root of x. We again take the natural log of both sides, use log properties to pull the power to the front, and simplify as much as we can. And take the derivative of both sides, getting 1 over y dy dx on the left, as you always will in logarithmic differentiation, and applying the product rule to the right. The derivative of the square root of x is 1 over 2 the square root of x times 1, the derivative of x, then multiplied by natural log of x, plus the derivative of natural log 1 over x times the square root of x. Notice that x and the square root of x reduce and give you 1 square root in the denominator, as you can see here. The next thing I did was I decided I wanted to go ahead and have a common denominator. So I multiplied the second term by 2 divided by itself. That gave me a common denominator of 2 square root of x and 2 plus natural log of x in the numerator. I cannot cancel the 2 because the natural log of x does not have it as a factor. I move the y to the right and replace it with x to the square root of x. Notice that because of the original definition with the square root of x, that I know that the value has to be greater than or equal to 0. The derivative, however, tells me that x cannot be 0. So in fact, for the derivative, x is greater than 0. I want to find out where it's going to be 0. X to the square root of x won't be 0 because x is not allowed to be 0 because of the variable in the denominator. That means that the factor 2 plus natural log of x, all divided by 2 square root of x, must be 0. That happens when the numerator is 0 and the denominator is not. We set 2 plus natural log of x equal to 0. And the next thing we want to do is switch to exponential form. This gives me natural log of x equal to -2 with a base of e, power -2, it equals x. The x coordinate of the point where the tangent line is horizontal is e to the -2. And I substitute that value into the original function, x to the square root of x, to get the y value, which I did not simplify. Let's now look at the graph so that we can verify our result. You'll see the point here where I have the point listed and the original function. When we're looking at this, notice that I have the horizontal line at the y coordinate there, and it does have a slope of 0. We have one last example to work, which is example number 14. In example 14, we're looking at an application problem. A radioactive isotope of the element erbium has a half-life of approximately 12 hours. Initially, we start at t equals 0 with 9 grams of the isotope present. Plenty to kill you. The half-life equation is given by Q of t equal Q naught, meaning the original quantity present, the 9 grams, times 1/2 raised to the power t divided by the half-life in hours. The half-life is 12 hours. So the first thing we'll do is we'll rewrite the function using the information we're given. That is what you're asked to do in part A. So in part A, we rewrite our quantity function as the original amount, 9 grams, times the base 1/2 raised to the t divided by 12 hours power. Notice that t carries hours, so the hours will cancel and just give us a constant. We have now related this exponential function to the original information that we have. We want to use that in order to find the rate at which the substance is decaying in t hours. In other words, find the derivative. In part B, we can compute Q prime of t by keeping the 9 as a constant and then using the rule for the derivative of an exponential. The base is 1/2. This is going to give me the exponential again, unchanged, 1/2 to the t over 12, times the derivative of the power t over 12, which gives me 1/12. When I simplify the 9 and 1/12, I get 3/4 times the exponential 1/2 raised to the t divided by 12 power. This is the rate of decay of the radioactive substance, how fast the grams are becoming non-radioactive over a period of time. We now want to determine the rate of decay at 4 hours. So we're going to substitute into our derivative formula 4 hours. This gives me 3/4 times a base of 1/2 raised to 4 hours divided by 12 hours, which reduces to 1/3. The 3/4 is a constant. It is not being raised to the power. Only the 1/2 is being raised to the 1/3 power. We forgot one thing. We forgot to multiply by the natural log of the base, since the base was not e. We should have a natural log of 1/2 in here. Oops. Times natural log of 1/2. When you work this out, you're going to get a rate that's approximately negative 0.4126 grams per hour. This means that 4/10 of a gram is non-radioactive for each hour at that particular point in time. However, the rate of change is a decreasing function, so less and less will be non-radioactive after the same 1 hour. This is actually the end of chapter 3 on derivatives. The next chapter is applications of the derivative, so we're still going to be doing derivatives for some time to come. We'll start off with what's called related rates. Related rates basically means taking a look at how one variable changes with respect to another, which means they're all applied problems. This is modeling the real world. Join me in the next video to start chapter 4 with related rates.